Okay, should we get started? So this morning I'd like to tell you about counting curves. And this is a basic introduction to work of Grisha McCullen. And it's this curve counting that really drew a lot of attention to tropical methods. He had some very nice results maybe 5 to 7 years ago that really received a lot of attention. And so I'd like to spend this lecture giving you a basic introduction to what this is about. So let's start with a very simple question. How many singular quadratic curves, singular quadrics, pass through four given points? Well, what's a singular quadric? Well, a quadratic curve that's singular, the only way a quadratic curve can be singular is if it breaks into two lines. So a singular quadratic curve is two straight lines, and it's very, very easy to see that both classically and tropically, through four red given points, they're precisely three singular quadratic curves, namely pairs of straight lines. Right? So you can pair up the four red points in three different ways. To any pair, there's a red line, and so therefore the answer is 3. So they're precisely three singular quadrics that pass through three given points. Now, singular quadrics, so a smooth quadric has genus 0. It's a Riemann surface. So in the discussion that follows, we should maybe think about singular quadratic curves as having negative genus. Okay, so should have genus -1. So that's a very easy, very, very easy answer. Now, those 3 points, of course, if you drop the word singular, you can say how many quadrics pass through four given points. Well, the answer is infinitely many. There's a line in P5 of quadrics passing through the 4 points, and we've seen that line. That line, like every line in tropical geometry, is a tree. And on that tree, there are 3 distinguished points. On that line, there are 3 distinguished points, namely those. Okay? Now, before we go on, let me point out that 3 is the degree of the discriminant of a quadratic form. So if we look at the quadratic form in the very first lecture, I said a quadratic form is given by a symmetric matrix. So I use this notation, So this is the determinant of the symmetric matrix that specifies the quadratic form is the determinant. Symmetric determinant is the discriminant. And it's this discriminant has degree 3. That's the same number 3. Right? So this discriminant is a hypersurface. So that's a hypersurface. And this sits in P5, right? We have this picture. So this is the picture of a 4-dimensional tropical variety with a 2-dimensional linearity space. We found this painfully yesterday evening together. And the number 3 is the degree of this hypersurface. So this line, the line of all quadrics that pass through the 4 given points is a straight line in P5, and it meets this cubic hypersurface in 3 points. Right? So these 3 intersection points, these 3 configurations are the intersection point of the straight line with this cubic hypersurface. Okay, very good. Let's start from the beginning. Let me give you a very brief review of 18th century plane algebraic geometry. So this is 18th century algebraic geometry. Okay, so in 18th century algebraic geometry, we have a smooth curve. So C is a smooth curve of degree D, and it had just been, projective space and the complex numbers had just been invented. People realized 200 years ago that if you draw figures in the real affine plane, things are very, very difficult. So therefore, to make geometric problems easier, 200 years ago, geometers invented the complex numbers, and so they replaced the real numbers by the complex numbers. And to make it even easier, they replaced the affine plane by the projective plane. So let's consider a smooth curve of degree D in the projective plane. Well, then we have its genus, which is the genus of the corresponding Riemann surface, so the genus of the corresponding donut, and that's a half d minus 1 times d minus 2. So a general smooth curve of degree D in the plane has this degree, d minus 1 choose 2. But for us, this number here, really, this is really the number of lattice points in the interior of the Newton polytope of that curve. Right? So the genus, this number, d minus 1 choose 2, is the number of interior lattice points in the Newton polytope. So Newton had been around, right? So 200 years ago, he was already around. He had invented the Newton polygon and calculus and lots of other things. And so we knew that the genus is the number of interior lattice points in the Newton polytope. So let's do a simple example. So let's say if D is 4, then G would be 3. So plane curve of degree 4 has genus 3, and here's the Newton polytope. So 1, 0, 1, 2, 3. So these are the lattice points. Whoops. No, I'm missing one. Try again. We want degree 4, right? So 1, 2, 3, 4. 2, 3, 4. 1, 2, 3. 1, 2. And so there we go, right? The number of interior lattice points, the genus of a plane curve of degree 4 is exactly 3. Okay, so that was known. Now, this is true for a smooth curve. Now, it could happen that the curve becomes singular. As you vary the coefficients and you move the coefficients from general coefficients to special coefficients, the curve can become singular. And what happens is that the genus drops by 1. The genus drops by 1 for each nodal singularity. For each nodal. So this is just an ordinary, usual double point. So this is the generic situation of a singularity. So, whoops, making a mess here. Oh no. This is designed for very short people, I think. Okay. So as the curve, becomes singular, it acquires, nodal singularities like this, and each time there's a node like this, the genus drops by 1. So on the donut, what this means on the donut that you will see at KAIST in the course this fall is you just squeeze the donut. You sort of pinch it together, right? You can imagine a donut and you pinch it, and then just when you make that transition, the genus actually drops by 1. Okay, and then one more thing was known. People talked about the space of all curves of a given degree. So the projective space of curves of degree d has dimension. That's a projective space. So first of all, the polynomials form a vector space, but two polynomials define the same curve if they differ by scalar multiplication. So we can pass to the projective space, and his dimension, and that dimension is d plus 2, choose 2, minus 1. So this is the number of all lattice points here, and minus 1 because we want to turn this into a projective space, and that's your number from the exercise yesterday. Okay? I'm going to take your number, I'm going to rewrite it a little bit. I'm going to rewrite it like this. I'm going to rewrite this number as a half. I want to pull out this genus explicitly. So I'm going to write it as d minus 1, choose 2, plus 3d minus 1. Okay, so you can check, well, I haven't done anything, right? The left-hand side equals the right-hand side. You just check that these two things are equal. And so here I have the genus of the general curve, and then I have an extra term, which is 3d minus 1. Okay, so that's very classical. That was well known 200 years ago. So now let's take the tape and fast forward to 1990. So let's talk about Gromovwitten numbers. So this is, 1990. Now, of course, I can't resist the temptation to make a polemic remark, right? So 4 years, 5 years from now, you're going to have the ICM in Seoul, so you'll be the center of the mathematical world. There'll be Fields medals and all that kind of thing. And so Gromov is a very distinguished mathematician who just won the Abel Prize. And Witten is at least as distinguished as a physicist, theoretical physicist who won a Fields medal. But Witten is sort of just one of many, actually. If you look at the last 20, 25 years of Fields medal winners, I would say a half of them have been inspired in some form or another by physics. Right? The connection between physics, theoretical physics, and mathematics, in particular geometry and topology, runs very, very deep. So, of course, it's a mutual relationship. It's like a healthy marriage. The relationship between mathematics and physics has been a very, very mutual relationship. So, of course, historically, you think people like Newton, the guy who named the polytope, and after him, mathematics has contributed to physics a lot over the years, but I think it's, again, fair to say in the last 25 years, it's the other way around. I think physics has contributed more to mathematics. And some people even say, algebraic geometry is a branch of physics these days. Now, that's wonderful. I'm going to talk about this. So because there's so many, many, many smart people doing this, both inside and outside Korea, I'm not doing it. I think biology is the next thing. So if you want to think 100 years ahead, or maybe 200 years ahead, I hope that the biology will be the next physics as far as mathematicians are concerned. Anyway, so let's stay at 1990 and let's talk about Gromovwitten numbers, and let's ask the following question. So what is the number? What is the number? Let's call it NGD of curves of genus G. Genus G and degree D that pass through a certain number of points namely that pass through G. Trying to be too clever here. That pass through G plus 3D minus 1 general points in the plane, in the projective plane. So that's our question. So how many curves pass through those many points? Now, it turns out that this is a meaningful question. And the reason this is a meaningful question is because we've written the dimension of the projective space exactly in this form, right? So if there are no singularities, so if the genus is as big as it can be, a half d minus 1, d minus 2, then the answer is 1. There's a unique curve, So if you have 5 points in the plane, there's a unique quadric, right? If there are 9 points in the plane, there's a unique cubic, and so on. So if you just put down as many points as you have dimension in the projective space, each point specifies a hyperplane worth of curves. And hey, we all know, right, the right number of hyperplanes in a projective space meet in a point. So that's easy. Now, as the genus goes down, we're enforcing nodal singularities. We're cutting down, we're saying there should be a nodal singularity, and there should be another nodal singularity. And that's a codimension 1 condition. So each time we are requiring the genus to drop by a certain number, then you're increasing the codimension. So if you drop down the genus by 5, right, then it's not allowed for all curves to run for competition. But then only, codimension 5 worth of curves runs for competition. So therefore, you're no longer allowed to plop down, put down the general number of points. You're only, allowed, the earlier number of points minus 5. Okay, so this is the expected, and that's okay. So this is actually works out okay. So this is just the dimension count that says that if you drop down, put down this many general points, G plus 3D minus 1, you expect a finite number. So let's see some examples. Well, the first example we saw in the high school lecture was N01 equals 1. Okay, so how many genus 0 curves are there passing through? So what's 1? So now we have to plug in, right? So you go 0 plus 3 times 1 minus 1, that's 2, right? So if N01 asks how many genus 0 curves are there of degree 1 passing through 2 general points, and the answer is 1. We learned in the first lecture that for any 2 points in the plane, and I mean it, for any 2 points in the plane, there's a unique straight line passing through those 2 points. That's our first Gromovwitten number. We also saw, in the high school lecture, that N02 is 1, right? So if now you take 2, that's the degree. If you have genus 0, so then this becomes 5. So this says for 5 general points in the plane, there's a unique quadratic curve passing through those 5 points. Now there's a reduced version, which I'm going to call N red. And you can actually do this with negative genus. So this number 3 over here can be interpreted as this number with genus minus 1 and degree 2 if you allow reducible curves. Although I'm not going to allow that from now on. So I'm not from now on going to assume, I'm from now on not going to allow this situation. I'm only going to look at, irreducible curves. Okay? So I'm not going to allow, reducible curves such as unions of 2 straight lines. Okay, and then let's go on. Let's look at cubic curves. Well, there's 1, 3, 1. That's still 1, right? You plug in. Okay, so that's genus 1. And then D is 3, so that's 1 plus 8, and that's 9. Okay? The question is, how many genus 1 curves of degree 3 pass through 9 given points? And the answer is 1, right? Because the general cubic curve has genus 1. So that's just the same as asking how many cubic curves pass through 9 given points, and the answer is 1. So that's not very interesting. But the next case is interesting. The next case is n03 is equal to 12. Okay, so this is the first interesting case. So the first interesting case says how many genus 0 curves of degree 3 pass through 8 given points. Okay? Now a genus 0 curve of degree 3 is a cubic curve with one singular point, with one nodal singular point. Okay? And the answer is 12. And we're going to explain this 12 in this lecture. And then you can go on, right? You can do Gromovwitten numbers for quartic curves. So n3, 4. So the general, so it always starts with the maximal possible genus. So for a quartic curve, the maximal possible genus is 3. 1, 2, 3. And there's unique curve passing through these 14 points. And then you go n, 2, 4. There's 27 quartic curves of genus 2 with one singular point passing through 13 points. And then n, 1, 4 is 225. And finally, the last one, n, 0, 4 is 620. Okay, so if you want a quartic curve to have genus 3, you have to force it to have 3 singular points. So, and the number of, and that passes then to 11 points. So the number of rational quartics passing through 11 points in the plane happens to be 620, and so on. Right? So these are the so-called Gromovwitten numbers in the plane. So McCullen proved the following theorem. I'm going to state this informally first, and then I'm going to state it formally. So it says the numbers NGD for any G and D can be computed tropically. Okay? So you can, there's a way of stating the same problem tropically, and it turns out you get the same number. The same numbers, 225 and 620, will come out. So what I'd like to do in the next 25 minutes or so, I'd like to explain what this theorem means. Okay, so I would like to make this theorem precise. Okay? Is there any question at this point? I'll start erasing. Okay, so let me first define smooth curves and singularities. So a tropical curve in the plane. So a tropical curve in the plane is defined to be smooth of degree d. So a smooth curve of degree d, if it is dual to a unimodular triangulation of the triangle, to unimodular triangulation of its Newton triangle. So the Newton triangle is simply convex hull of the origin, 0d, and d0. Okay? So what's a unit triangulation? A unimodular triangulation is a triangulation using the given lattice points where each triangle in the triangulation has area half, is as small as possible. Okay, so here is an example for cubic curves. So here is an example of a unimodular triangulation. So anyway, to cut this up into unit triangles is a unimodular triangulation. So all triangles have the same area, namely a half. And then there's a corresponding dual curve. Right? There's a corresponding tropical curve corresponding to this picture. There you go. Okay, so here's one where you have an 8th cycle in the middle, and we had the team, I think, on the first day who showed us that you can have triangles and you can have any kind of cycle length for this kind of a smooth cubic curve. And then, we rotate. This is a max plus picture, but since we like the min plus algebra because we like valuations, we have to rotate the picture by 180 degrees. Let me write A for the number of bounded regions. I'm sorry, G, the genus, is the number of bounded regions. Okay? So earlier, so we saw, in general, so the number of interior lattice points is the genus of the curve, and that's equal, to the number of bounded regions in the complement of the curve. So that's the genus. So for a smooth curve, according to this definition, the genus is exactly, our genus. So you have exactly a half d minus 1 times d minus 2 cycles. I'm going to say a tropical curve is simple. So the tropical curve C is a simple curve if its subdivision, if it's not quite smooth, but the singularities aren't too bad. So if its subdivision, the corresponding subdivision of the Newton triangle has only triangles, possibly of larger volume. Okay, so has only triangles and parallelograms. But the triangles now are in a simple curve, so I'm not allowing pentagons and so on. But the triangles are now allowed to have possibly larger volume. So if I have a curve, so that means in the subdivision, I see maybe, I see a triangle is allowed, possibly a volume larger than a half, and then I allow parallelograms like this. So in the curve, you would see this kind of situation, and you would see, 3 valent nodes. So what this says, that in every node in the graph is either 3 valent or it's 4 valent, but locally it looks like the crossing of 2 lines. Okay, so that's such a curve I'm going to call a simple tropical curve. Now I'm going to define the genus. So the genus of such a curve, genus of a simple curve, genus of a simple curve C is going to be defined as a half T minus a half R plus 1, where T is the number of triangles in the subdivision. It's the number of triangles, and R is the number of unbounded edges in the curve. Okay, that's just a definition. So this says for a simple curve, I'm going to define the genus to be a half t minus a half r plus 1. It's a little exercise to show that that's a non-negative integer. Okay, that's actually not just a half integer, but it's a non-negative integer. And also, this definition is consistent. So in the smooth case, it gives exactly the right thing. So in the smooth case, dt is d squared, right? So in the smooth case, they're exactly d squared triangles, right? So if you have a triangle of side length d, right? So the area of a triangle is a half base times height. The standard triangle has area a half, so they're exactly d squared triangles in a smooth unimodular triangulation. And also the number of unbounded rays is 3d, and that's the genus again. So that's a d, so that's our old number, right? So if you plug this in, so if you plug in this for t, and you plug in this for r, and you factor it, you get a half d minus 1 times d minus 2, which is exactly, the 18th century genus of a smooth cubic curve, plane curve, degree d curve. Okay. The last definition we need to assign a multiplicity. We need to assign a multiplicity to a simple curve. So the multiplicity of a simple curve, C, is the product, is defined to be as the product of the normalized areas, of all the triangles that you see. In the corresponding triangulations of the new triangle. What's the normalized area? Well, it's twice the usual area. So the area is normalized so that a triangle, a primitive triangle of area half is measured with area 1. Okay, so that's the normalized area. So to count the multiplicity of a simple curve, so if all the parallelograms that we see, they will correspond to the nodal singularities, so they don't contribute. We're going to disregard the parallelograms, but we're going to look at all the triangles, and if all the triangles are unit triangles, then the curve counts with multiplicity 1. But if some of the triangles, have higher area, are not unit triangles, then, could happen, right, that we have a triangulation where we're using some larger triangles, such as this one, and you need to actually calculate the normalized area. So that's a half, So it's the area of a triangle, the normalized area is base times height. And I guess this is a triangle of normalized area 3. Okay, very good. So that's the multiplicity. Now this this area that we're using, can also be seen directly in the yellow curve. Can be expressed as W1 times W2 times the determinant of U1, U2, where W1, W2, and W3 are the weights and U1, U2, U3 are the primitive directions emanating from a node in the graph. Okay, so what I'm saying is, suppose we're somewhere in the tropical curve, so a triangle in the subdivision will correspond locally to a picture like this, right? So then we have, the primitive vectors in these directions, These are the primitive vectors, and that's, u1, u2, and u3. But there's also weights, right? When you run GFan, kindly for us, GFan also outputs weights on each maximal cone, and those are the weights. So we have this is a balanced situation, which says that the weight W1 times U1 plus W2 times U2 plus W3 times U3 sums to 0. Okay? And then it turns out, if you look at two of these, you look at this number, you form it, that's actually the normalized area of the corresponding triangle in the dual picture. And then this doesn't depend on the choice of indices. You could take 1 and 2, or 1 and 3, or 2 and 3, and the independence of the choice of indices is equivalent to the balancing condition. Okay, that's another way to say the multiplicity. Okay, so here's a theorem again in more precise form. In this case, says the following. So the Gromovwitten number NGD is equal to the number. So this is the number from classical, projective algebraic geometry. This number equals the number of simple tropical curves of degree D and genus G. So genus according to that definition, so according to this definition, passing through the right number of points. Passing through G plus 3D minus 1, general points, generic points in the plane. In TP2, but you have to count each curve with this multiplicity, where each curve is counted with its multiplicity. Well, that's the theorem. So that theorem says, that's the precise form of this theorem. So here when I say the Gromovwitten numbers can be calculated tropically, this is exactly what I mean. You can just set up a purely combinatorial definition, which I did over there, and then just counting, tropical curves of the right genus passing through the points gives you exactly the correct number, will give you the same 620 that you would have in the classical count. Okay, so that's the correspondence theorem. So, well, maybe one word about generic, because Jessica just asked. So what does generic mean? Well, for instance, you could pick your points, and we'll see this in the handout. They could lie on a classical line. You could pick your points on a classical line with general enough slope, let's say with irrational slope. Now, why is that? Well, in algebraic geometry, one way to pick generic points is to pick a monomial curve, to pick a toric curve with very general exponents, like t to the 17th, t to the 19th, t to the 63, something like this. And then you just pick a bunch of points on this curve. So picking, general points on a toric curve will give you generic points. Well, it's going to be certainly generic if the exponents are irrational, right? So if you pick a monomial curve with irrational exponents, that's going to give you generic points. But, that's going to tropicalize. If you have a monomial curve, a toric curve in the tropical picture is a classical straight line. That was our definition of toric variety. So variety being toric means that its tropical variety is a classical linear space. So therefore, we're going to pick our points in a configuration that doesn't look generic, but in fact is very generic. We're going to pick them on such an irrationally sloped line. Now, McCullen's approach to this is very geometric. So he derives these things using symplectic geometry and topology arguments. In the meantime, there are other approaches. So there's work that's a bit more algebraic. So I'm maybe it's a bit more familiar to me. So in particular, I like to advertise some subsequent work so a newer approach to this was taken by Andreas Gartmann, and his collaborators, in particular his students. He's a very, very popular advisor in Germany. And he and his students, which include Allermann and Rao and many others, and they propose a more algebraic approach based on tropicalizing moduli spaces and developing, so to build a tropical model of the corresponding moduli spaces, and then to develop the relevant intersection theory. And we talked a little bit about this yesterday afternoon. So his students, Allermann and Rao, have this nice paper on first steps towards tropical intersection theory. But before that, there was a line of work. So let me give you a typical result. So a typical result from the Gartmann school. So this was proved by Andreas Gartmann and Hanna Markvik. So this is H. Markvik in 2007. And this was actually, this particular statement I'm going to state right now was known before. So this was proved before in the classical setting by Manin and Kontsevich in 98. But so this is quite a recent subject. But what's nice about the Gartmann-Markvik theorem is that it's a purely tropical theorem. So it's just purely, using piecewise linear methods. And so let me state this result. So this is the tropical W, D, V, V equations. And it says the following. So this is just on rational curves. It's a special case. So the number which I just call ND, which is N0D. So this was the rightmost number in our column. The one when you want to count with the most singularities, with the lowest genus. So this is the number of genus zero curves of degree D, passing through the right number of points. So N4 was 620. N3 was 12. So that number, so this is the number of rational curves of degree D through the right number of points, 3D minus 1 points, satisfies a certain recursion. And I'm going to write this down for you, So it's pretty complicated, but let's write this down. So this says ND. So ND can be calculated in terms of smaller NDs. And what you do is you take the sum over all pairs of positive integers D1 and D2. So you look at all possible ways of splitting D as a sum of positive integers. And then there's some crazy coefficient, d1 squared, d2 squared times 3d minus 4, choose 3d minus 3d1 minus 2 minus d1 squared d2. Hope I got this right, copied this right. 3d minus 4, 3d1 minus 1. So that's the multiplier. And then the whole thing times the product of the two earlier numbers. So this whole multiplier times nd1 times nd2. Okay, so that's a typical example. And so this lets you calculate, the number 620 in terms of earlier numbers, okay, in terms of 12 and 1 and so on. Okay. Now, what's nice about the Gartmann-Markvik proof is, so there's a recursion, and this corresponds to explicit degenerations. So you have these points in the plane, you have the curves that pass through them, and basically you degenerate the picture, you break it into smaller pictures. And this has a purely pictorial proof. So they give you a proof, they explain. Every term in here has an explanation in terms of tropical curves passing through points in the plane. Maybe a few more sociological remarks. So I mentioned Hannah Markvik earlier. So there are actually two Markviks. There's Thomas Markvik, her husband, and Thomas wrote the singular library. And Hannah, she was the student of Gartmann. So she worked with Gartmann, and so they're also working together. What's maybe a little bit interesting, since there's the women's conference going on right now, so he changed his name to take her name. Okay, so in the Western, unlike in Korea, in Europe, Germany, it's common for couples to have the same last name, and so he had a different maiden name. Okay, I don't know how you call this. Right, so, the other sociological remark concerns WDVV. So these are the initials of physicists, right? So we just agreed that algebraic geometry is a branch of physics. So this is Witten, Digraph, Valinde, and Valinde. So there's Markvik, and there's Valinde. Okay, so what else? Now, we can use Mikulkin's technique to calculate these numbers in general. So we can actually do this. And for higher genus, there is not quite such a clean formula. But we can do, so Mikulkin has a nice technique. So he refines his correspondence theorem. So we can use Mikulkin's technique of so-called increasing lattice paths. So he has a technique which he calls increasing lattice paths, which is a way to calculate, to count these curves and to group them together, to organize these curves into meaningful groups if you place your points in this particular way. So these increasing lattice paths, this increasing comes along the line with the irrational slope, and that's a very nice technique. And since a picture says more than 1,000 words, the last 12 minutes of this talk will be mostly pictures. So maybe I'll pause. Is there a question or disagreement? So please feel free to strongly disagree with my views.
Can you tell us one more time why we don't consider Taylor algebra, maybe consider the multiples?
Well, I didn't tell you at all why. Okay? Yeah. So I didn't tell you why. Let me give you my philosophical answer. So, I think if Mikulkin heard me, he would hate it. But let me give you my answer. Okay? So let's take, what we're really doing is we're doing an intersection, we're doing a certain count on a moduli space. So there's some big moduli space of stable maps of curves out there with certain properties, and we're intersecting this moduli space with some conditions. We want to count, want to find out that the number of intersections is 620. Okay? But you know, on this moduli space, which is out there in Never Never Land, this is a tropical variety, right? So why is this a tropical variety? Well, because this moduli space is a projective variety. It's given by algebraic equations, lots of them, in many variables, right? So problem with these moduli spaces, they might be projective varieties, but the equations you need to write them down, there are lots of them in lots of variables. But let's say we have a friend on Mars with a big computer who can calculate this for us. So we ask our friend on Mars, give us the equations for the appropriate moduli space. Then I'm going to give these equations to you. And we wait a couple centuries, and out comes the output of GFAN. And GFAN kindly lists each maximal cone with the multiplicity. And that's the multiplicity. Yeah? So each of these configurations corresponds to a particular cell in that, you know, hypothetical GFAN output, and it so happens that that's the multiplicity that's being output. Does this answer your question?
No, I mean, my question
No.
is why do we discard the
It just so happens that they don't count. So when you do the analysis
Right, but
on...
you just say that because we may end up doing a normalization of curves so that the
Pardon me?
maybe I just misunderstood. That the crossing sort of corresponds to the
Yes,
point.
that's right.
So if we consider the normalization of the curve,
No, we...
okay.
I see. The question is whether we consider the normalization. Not really.
Okay.
Not really. So, yeah, so each of these, I mean, after all, there's a fundamental theorem, right? So if this comes with a multiplicity, basically what happens, if you have these triangles of large area, they lift to several, you know, classical solutions. So when you go back up and lift, you know, that would win you a big brownie if you did that. But so then you lift them to classical curves up there, and it just so happens you have to take the triangles into considerations, and the quadrangles don't count. Okay. Okay, let's look at the picture that I handed out. So this is a particular count of 12. So here we have 8 generic black points in the plane. Everybody got the handout? So we have 8 points in the plane. They are on a line with irrational slope. So they are in generic position. And I've drawn for you, you know, the 12 curves. Well, there are 9 pictures. So there's one curve, curve number 6, that has multiplicity 4. So it turns out that the curve 6 has multiplicity 4. Every other curve in this example has multiplicity 1. Okay? Now, you can see that, you know, this multiplicity 4 comes from 2 of the triangles that are adjacent to this double line. You see in the middle there's sort of, I indicate a little double line, and the 2 nodes at the end of those, they will be triangles of area 2. So there we have to multiply 2 times 2 equals 4. So you can look at these pictures and you can enjoy them, right? So this is, you know, this is the solution. So these are exactly the 12, you know, cubic curves. You can see they all have exactly 1 nodal singularity corresponding to 1 parallelogram in the triangulation, and that's it. Right? So you can construct them. And what McCullen does, these lattice paths, well, they are a convenient technique for grouping them together. So it turns out you can take those 9 curves and you put them together in 5 groups. So the way you do that is I've indicated that at the bottom. In the first page I said there's a lattice path. I say multiplicity 2. Well, these are sort of paths in the triangulation. These are actually paths from the upper left to the lower right, along increasing in the irrational direction in the triangulation. And then each increasing lattice path is in one-to-many correspondence with curves whose triangulation refines the lattice path picture. And that gives you a more effective way. So, you know, if you want to code this, right, so of course it's fun to do these things, right? So on your computer, the students, right, they might like to write a little Java applet that runs on their device, right, where you plop down 8 points and boom, you know, they all come out. And when you write that program, it's efficient to use the lattice point technique to quickly get these. So that's that. So these are the 12 singular cubics passing through 8 given points in the plane. There are questions? We still have 6 minutes, so let me say a few more words how I like to think about this. Okay. So the way I like to think about this picture is as follows. Let's forget about the singular point. Let's look at the family of all cubic curves passing through 9 points, right? So how would that look like? How would the picture look like? Well, we have all cubics passing through 9 points. That would be a tree with 10 leaves, right? That would be a line in P9. That would be a straight line in P9. So we're going to draw that as a tree with 10 leaves. The 10 leaves are the taxa, right? The taxa are not the fugu fish and so on, but they're the monomials of degree 3. Right? So we have a tree whose 10 leaves are the monomials of degree 3. We run the neighbor joining algorithm, for instance. Yes, I do like biology. Right? So we run the neighbor joining algorithm, and then we get this line in P9 of all cubics passing through the 8 points. Now then we take that line and we intersect it with a discriminantal hypersurface. There's a discriminant, which is a hypersurface of degree 12. And then, that straight line goes beep, 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 beep. It meets that degree 12 hypersurface in 12 points, namely these points. Right? So these 12 are the intersection points there's a line worth of these pictures. There's a tree worth of these pictures. And it meets the discriminantal hypersurface in precisely 12 points. And the reason is because the discriminant has degree 12. Okay? So that's why the last lecture today will be about discriminants. So I like to focus on this from the point of view of discriminants. And I like to end on the last by showing you the solution to the last exercise problem that we didn't discuss yesterday. So let's go over this. So this works not just in projective space. This works on any toric surface corresponding to families of sparse polynomials. So let's take this sparse family of plane cubics. So this corresponds to a family on a toric surface that's gotten by blowing up 3 points in the plane. So the homework is A, compute the Newton polytope of the discriminant of this family. So first you calculate the discriminant, you look at its Newton polytope. Of course, this hypersurface of degree 12 is the tropicalization of this discriminant. And we learned yesterday, painfully at 6 p.m., how to read off the tropical hypersurface from the Newton polytope. Right? We built the Newton polytope. Now we have a high-dimensional Newton polytope, and then we read off the hypersurface, which we called the Toblerone yesterday. Part B, how many rational curves of the above special form pass through 5 general points in the plane? Draw a picture that demonstrates the tropical solution, and so on. So Dustin Cartwright, who's a student, came up with the following. So first of all, we calculate the discriminant. So this is a little piece of singular code that calculates the discriminant. Okay, so here's this polynomial with now he calls the coefficients a, b, c, d, e up to g, and then we say he asks singular the question, under what condition on these coefficients does the curve have a singularity, a nodal singularity, and then singular comes back with the answer. And it turns out, in this case, also the degree is 12. And then by a computation polymake, turns out the Newton polytope is a 4-dimensional polytope with 127 vertices, 65 edges, and 12 facets. So then B, a general cubic polynomial, has genus 1. It's rational if and only if it has a singularity. Passing through 5 general points imposes 5 independent conditions on the coefficients, thus the coefficients are in the intersection of the discriminant with 5 hyperplanes. Since the discriminant has degree 12, the intersection is 12 points. In other words, there's 12 rational curves of the specified form. So in this case, it so happens that on this surface we also have a Gromovwitten number of 12, and then he makes the picture. So I chose 5 points, which each differ from the previous one by, so he picks them on a line. Now that line doesn't really have irrational slope, but it turns out it's good enough. You know, you try it, it turns out, and then, okay, so you can enjoy this, right? So these are the curves that he gets, and so they are, with the right count, you know, there are altogether 12 of this family of curves with one singularity that pass through. Okay. Okay, so I think it's time for coffee break. You can enjoy these pictures. On the solution set, there's more stuff, right? I know that people in Seoul really like representation theory, you know. So Georgia Bankart is giving the main talk across the street. So cluster algebras is a hot topic in representation theory and related fields these days. So one of the questions was to write a short essay, how are cluster algebras related to tropical geometry. So you can read these things online. So, okay, let's have coffee, and then the last lecture at 11 o'clock will be about discriminants.